So, we're going to be talking today about forces, and we're going to be talking about the relationship of forces to acceleration. From yesterday, we discussed the accounting of forces. If I have an object that has different forces acting on it, like so, then we are going to accumulate all these forces with our net force, F net, which is simply the sum of all the forces acting on the object. And that sum is a vector sum. So just to be clear about this, we'll put our vector hats over this so that we understand that the forces will sum separately in the x and y directions if we're thinking about it in rectangular form. Newton's laws were very interesting. We just did a sort of a sophisticated data collection process where we observed that force was proportional to acceleration. Newton didn't have that ability to collect data. And so what he does is very approximate. And he ends up, honestly, fudging the data a little bit by smoothing out the noise. But his conclusion is really summarized in 3 laws. And the first of those laws is this. And in terms of understanding physics, these 3 laws are the kinds of things that you want to like tattoo on your eyelids because they're really fundamental and basic. And the first can be expressed like this. In an inertial frame, if the net force on an object is 0, then the acceleration of that object will be 0, and vice versa. This is commonly stated in words like this. An object in motion continues in its motion. An object at rest stays at rest unless acted on by an outside force. Unless acted on by an outside force. If and only if. It means it goes both ways. If you see an object not accelerating, you know that its net force is 0. If you see an object whose net force is 0, you know that it will not accelerate. Yeah, there's a couple of subtleties here that I want you to observe. The first is the qualification in an inertial frame. If our reference frame is an accelerating frame, Newton's first law will fail to hold. And we're going to have to account for that later on. But we do remember the bolt problem, where we dropped the bolt in the accelerating car, and mysteriously the bolt experienced an acceleration in the x direction, even though it had no forces acting on it in the x direction. And that was an artifact of our accelerating reference frame. So this applies to inertial frames only. Another way of putting Newton's first law profoundly is there exist inertial reference frames. So the first subtlety is this applies only to inertial reference frames. The second subtlety is the word outside force. And that is expressed in terms of our free body diagram. I want you to imagine for a moment that we take a much larger lab cart, and on it we put Will and Josh. I'm not telling you which one's but that one. So now Will and Josh start fighting over Will's ubiquitous sweatshirt. And, right, exactly. And so Will starts pulling on Josh and Josh starts pulling on Will. Which way will the cart accelerate? Answer, it does not. Because, in terms of the system that we have right here, this system is not being acted on by an outside force. Okay? So if there is an F Will Josh, and there's an F Josh Will, then these two forces are internal to the system, and they will not cause the system to accelerate.
Because they're off the car.
Because they're on the prospect accelerator.
So that way, one's like attached to like.
Your legs are like to the side. They're like to the right of the left.
Does that make sense to everybody?
Yes.
So we want to distinguish between forces that are internal to our system and forces that are external to the system. One way to be, I've used this word system. What is this word system? A system is a collection of objects. An isolated system is a collection of objects that we can draw a dotted line around, through which there is no force. Objects not acted on and one of the things we're going to train our eyes to see is going to be the distinction between these outside forces and these inside forces, and the way that we would do it is through the process of drawing free body diagrams. So that's Newton's first law. Well, what if F net is not zero? Newton's second law. Here was Newton 1, and I'm going to abbreviate this in 1 for Newton's first law. Newton's second law. If there is a net force, then it is proportional to the acceleration, and the proportionality constant is the mass of your system. So here I've got an object that is acted on by net force, and as a result, that object is going to experience an acceleration. Notice that because this is a vector equation here, this is actually saying two things. It's saying that the magnitude of the acceleration is going to be equal to the magnitude of net force divided by the mass. And it is also saying that the acceleration vector will be parallel to the net force. The direction of the acceleration is always in the same direction. Can it ever be anti-parallel? No, not unless mass can be negative. But observe also weirdly that if our mass were to be zero somehow, then it would require no force at all to accelerate that object. And so in circumstances where we have things of negligible mass, you have to be alert to the fact that those objects of negligible mass will accelerate with negligible forces. Right? So Newton 1 and Newton 2 really tell us about the net force. Newton 3 is a little different. Newton's third law is going to be a law about the creation of free body diagrams. And that law is this. The force that A exerts on B is always equal but opposite to the force that B exerts on A. Or another way of putting it in words, you may have heard for every action there's an equal and opposite reaction. I don't like that because it's not precise enough for our purposes. Let me put it like this. Forces always occur in action-reaction pairs.
I'm sorry. Is that like the magnitude of acceleration is magnitude of
The net force, yes, sorry. Net, yeah. I do the net force to emphasize that what we're doing is we're taking a lot of different forces acting and just putting them all together into one. But the way I prefer to write F net is sum of forces, and you'll see me do that a lot. Look at this quantity and think of it as taking all of our forces acting on the object and just lumping them into one net force. Okay, so forces always occur in action-reaction pairs. Let's go back to our epic struggle over the sweatshirt. And if we now isolate Will, and we now isolate Josh, then we can draw the following forces that are acting on Will. First, there will be a force of gravity pulling him down. There will also be a normal force. We're going to call these 1 because Will is 1 and Josh is going to be 2. No prejudice. No prejudice towards numbers is implied here. Okay, good. All right. See, the Kaglets would immediately be like, I want to be number 1. Okay. And now there is going to be a force that is acting on Will that is coming from Josh, and that force is going to be this way. Force of Josh on Will. As soon as I draw the force of Josh on Will, Newton's third law kicks in and allows me to draw an equal but opposite force of Will on Josh. And this is where you have to be careful in your thinking. Will is the one exerting the force. Josh is the one receiving the force. The arrow goes on Josh. Josh is the one exerting FJW. Will is the one receiving FJW. That arrow goes on Will. So that your action and reaction pair always show up on different objects, never on the same object. Two different free body diagrams always. Let's complete our diagram because we've got more here. We've got Fn2, and we've got Fg2. And depending upon the nature of that lab cart, we may or may not have frictional forces involved. Perhaps they are struggling on a well-oiled lab cart or something. Okay? Now I want you to observe something. And that is, in my diagrams, I can see an action-reaction pair. I can see an action-reaction pair. What I cannot see is the action-reaction pair for Fg1 or the action-reaction pair for Fn1. Why not? Because my diagrams are not showing the objects that are exerting those forces. What object is exerting the force Fn1? The cart. And what object is exerting the force Fn2? Also the cart. So if I were to do a free body diagram for the cart, I would have an Fn1 pointing down automatically and Fn2 pointing down automatically. Notice that I'm giving these the same symbols because they have the same magnitudes. Remember that magnitudes are shown, but I'm giving them opposite directions because they are equal but opposite. What about the force of gravity? What object is exerting the force of gravity on Will and on Josh? The Earth. So to get the action-reaction pair for those forces, I would need to show the planet in my free body diagram. And drawing not to scale, here's the planet.
That's good.
And here comes FG1, and here comes FG2, just like that. Notice the implication. Will and Josh and all the rest of us are pulling upwards on the Earth with a force that is equal but opposite to the force that the Earth is exerting on us. Wait a second. Hang on. Is that really right? Am I really pulling on the Earth just as strongly as the Earth is pulling on me? Yes. Then how come when I jump off a chair, I move and the Earth doesn't?
What?
When I jump off a chair, I feel like what's his name in the movie? Oh, shoot. The actor who died, Robin Williams. Dead Poets Society, right? Standing up on a chair. Okay, here I am on the chair, and I jump. And when I jump, I fell to the ground. The ground didn't move. Did you feel the ground move? I didn't feel the ground move either. How come that happens if the forces are equal but opposite?
I mean,
Ground moves in your Earth,
Like you would.
Well, the ground did move in my reference. That's a good point.
The difference in masses.
Back to Newton's second law.
Oh, snap.
Back to Newton's second law.
no,
Right here.
1987.
The weight, the force of gravity on me is going to be proportional to my acceleration, and the proportionality constant is my mass, which is somewhere around like 70 kilograms, okay? The force equal but opposite on the Earth is going to be proportional to its acceleration, and that's the mass of the Earth. 5.8 times 10 to the 24th kilograms.
That's where I got it.
Which means the Earth did accelerate, but at a rate of 10 to the minus 23rd-ish meters per second squared.
what is,
Oh, that's not even measurable.
Ugh, not
Ah,
that big.
now we understand. So,
everyone?
when the fly hits the train, they exert equal but opposite forces on each other, but only one of them accelerates.
Poor fly.
You see? And it's because of their masses. So you're gonna have to train your mind to think carefully like this, because our tendency is to think that the train exerts a force on the fly, but the fly doesn't exert a force on the train. Nope, that's wrong. They exert equal but opposite forces on each other, but they do not have equal but opposite accelerations because of Newton 2. Does that make sense? Good. Well, this is going to be our framework for analysis. Believe it or not, I just taught you everything in this chapter.
Awesome.
So we're gonna have a test tomorrow?
Yeah, this test tomorrow, and you derive all the
Saturday
principles.
tests.
Or maybe we'll practice a little bit first. And here's where we're going to practice. What these three laws do for us is they give us a framework for problem solving, and our framework is going to be like this. If I want to find acceleration of an object, then I'm going to first create free body diagrams, carefully showing the forces acting on the object, and I'm going to apply and in particular, I'm going to use Newton's third law as a guide to my free body diagrams. So this is going to be a big deal. And then we're going to apply Newton 1 or Newton 2 as applicable in order to determine the acceleration of the object. Well, Newton 2 is going to help us find acceleration. Newton 1 is going to help us find unknown forces. So Newton 1 is useful when I already know that the acceleration is 0. Okay? Now, what we're really doing, just to connect this back to previous work, when I'm finding acceleration, what I'm doing is finding the second derivative of the position. So when I find the acceleration, what I'm doing really is setting up a differential equation. And in theory, I can solve that differential equation in order to determine the position or velocity of the object. So the big picture is Newton's laws give us a model for the motion of the object, and that model is expressed in terms of a Diffie cube. Does that make sense to everybody? And this is literally how the professional physicists think about it. Are we good? Okay, good. Next week, we'd like to actually make this happen.
Yeah, right.